Okay, we're going to cover something in this lecture that is a brilliant technique for proving that something is true for all integers. Okay, and it's called mathematical induction. Let me write down for you what we call the principle of mathematical induction. Okay. Suppose S of 1 is true. So in this case, S of n is an open sentence. Okay, let me write that here, just as a note. Okay. S of n is an open sentence. Okay, now suppose S of 1 is true and, comma, for any integer. Oh, actually, sorry, I've been saying integer, and I should have been saying natural number. For any natural number k, if S of k is true, then S of k plus 1 is true. Then S of n is true for all natural numbers n. That's the principle of mathematical induction. Okay, so the idea is this. You show that S of 1 is true. Okay, and then this phenomenon here, if S of k is true for some natural number, then S of k plus 1 is true. So that means because of that, and because of the fact that S of 1 is true, then S sub 2 must also be true. And then because S of 2 is true, then S of 3 must be true. And that causes S of 4 to be true. And that causes S of 5 to be true. And so on and so on and so on. And so then S of n is going to be true for all natural numbers n. Okay, it's very easy to see what's happening here if you visualize some dominoes. Okay, look at that picture. It's right out of the book. The only thing is, instead of parentheses, they use subscripts. Okay, that's all. So they've labeled each domino S1, S2, S3, and so on. And for this analogy, we're going to say that being true means the domino falls down. Okay? All right. So we have the domino set up. Now, if you just set up dominoes and push over the first one, does that mean they will all fall? The answer is no, because maybe the dominoes are spaced out too far from each other, right? Okay. On the other hand, if the dominoes are close enough to each other to knock each other down, does that mean that they will all fall? The answer is no, because you have to start it off manually. But if you put those two together, if you push over the first domino yourself, so that is analogous to S1 is true, and If the dominoes are all set up next to each other close enough that each domino will knock down the next one, that is analogous to the green highlighted sentence. If you have both of those together, if you push over the first one manually and each one knocks down the next, then they will all fall down. Right? It makes sense when you think of it like that. So if you have a statement and you wish to prove that it is true for all natural numbers, then you can use this idea, okay? And here's how you do it. So suppose you have this task. Prove S of n is true for all natural numbers n. Okay? So the way you can do it is you have two parts. Okay, just like the principle of mathematical induction has two parts. And then you get to make a conclusion. Okay? So step one, you show S of 1 is true. That's something that you do manually, meaning you prove that S of 1 is true. It's usually not difficult. Okay? And then step 2, you show that if S of k is true for some natural number k, comma, then S of k plus 1 is true. Okay, now, how do you do that? That's a conditional, right? You see the words if and then? So that's a conditional. So how do you prove that? Well, usually you can do this directly, and so that means there's going to be a part A and a part B. Okay, so part A is suppose S of k, S of k is true for some natural number k. And that part right there, I want to make this very clear, that requires zero work from you. It is a supposition. So all you have to do is write it down. Okay? Part B, you have to do yourself, which is show that S of k plus 1 will then be true. Okay, and then you have your, if you do step 1 and you do step 2, which means write that down and show that, then you can make your conclusion, which would be S of n is true for all natural numbers n by the principle of mathematical induction. We're just going to write by PMI. Okay? And the strategy is the same always for these. Okay? Now, you don't have to always start at 1. There are some things that are true. Let me just make an example. There are some things that are true for every natural number except, let's say, 1, 2, and 3. But starting with 4, every natural number after that, a statement might be true. So in that case, instead of starting manually with show S1 is true, you would start with show S4 is true. That would be your starting point. And then when it says suppose SK is true for some natural number K, it would be suppose SK is true for some natural number K equal to or greater than 4. Okay, but most of the ones we do, we're starting with 1. Now, a couple of these have names that you should really know. That first step is called the base case. Okay? And part A of the second step is called the inductive hypothesis. The base case is usually easy. The inductive hypothesis is always easy because there's nothing to do except write down the sentence. So 90% of the work is usually in step 2B, and it's usually not hard. Okay? All right. Now, how do you go about writing it down? I've seen students learn to do it many different ways. Okay? And some of those ways produce bad habits and some don't. So I'm going to give you a way that I want you to do it. And that is using the language of set theory. Okay? So here's how I want you guys to do this. Okay, so once again, let's say we have a statement S of n, and we want to show that that's true for all natural numbers n. Okay, so prove S of n is true for all natural numbers n. So here's how I want you to do it. So what's the first step? Let's look up here again. The first step, called the base case, is show S1 is true. So here's how I want you to write it. Okay? I would like you to start your proof. Let's write proof. Okay? I want you to start by saying, let A be the set of natural numbers such that S of n is true. Okay? And then I want you to show that 1 is an element of the set A. Of course, you don't have to call it A. That's fine. Call it anything you want, okay? Except capital S, because we're using that for the statement. So I want you to show that 1 is in that set. That's your base case. Okay? And then I want you to, this is literally just writing down a sentence. Suppose K is in A for some natural number K. That's your inductive hypothesis. And then I want you to show K plus 1 would have to be an A. And then you can make your conclusion. Therefore, A equals the set of all natural numbers. And then you'd be done. That's how I want you guys to write it, okay? If you use this language of set theory, meaning take the set of natural numbers for which the statement is true, and write that as a set with set builder notation. And then to say that the statement is true for a number just requires then to show that that number is in the set A. Okay? When you do your inductive hypothesis, all you have to do is say, suppose some natural number k is an element of A. So we're using the language of set theory. Okay, and it will help you a lot and sort of keep you from developing some bad habits that I see a lot of. And then we can conclude that A is all natural numbers, meaning the statement is true for all natural numbers. Okay? These bad habits I'm talking about are habits that students get into writing where if you then take their writing exactly as written, it is not logically true. Okay? They get into the habit of cutting a couple of corners here and there that they don't even realize they're cutting. They think they're doing it exactly the way they're supposed to. But then when you read it back, critically, meaning I'm just going to read what's written here and go by exactly the way it's written, then you can find a couple of mistakes. And it's really hard to get them to understand why there's a mistake there because they think they've done it correctly. So the best thing to do by far is to be in the habit of not making those mistakes in the first place so that they don't even develop, okay? It's much easier, rather than trying to break a bad habit, it's so much easier to just not let these habits develop in the first place. And I have found by doing your induction proofs, using the language of set theory, I find that it really, really clears things up for students once they get used to it. It's very, very awkward for students to start doing it this way if they have learned to do induction without using the language of set theory, and then you tell them to please start doing it this way. It's very hard for them to get their mind wrapped around it. But I'm showing this to you right off the bat, and I'm saying, okay, as soon as you start learning how to do induction, do it this way, and I think you will be very well served by it. So that's the way I want you to do it. If you have other professors that say you can do it other ways, then that's fine for their classes. But for my class, I want you to do it this way. Okay? All right. So let's practice it a few times. Let's prove this very, very well-known formula, which is if you take the sum of the first n natural numbers, so the sum of I goes from 1 to n, that means 1 plus 2 plus 3 and so on up to n. There's a very famous formula you probably know. I don't know. It's n times n plus 1 over 2. Okay? And that's true for all natural numbers. Okay? And there's more than one way to prove this, but the easiest way is using induction. Okay? So let's prove this. And I'm going to write it out so you can see what I mean when I say I would like you to write it this way. Okay? So I'm going to start by saying let A be the set of natural numbers such that the sum of the natural numbers up to that point equals that number times the next natural number divided by 2. Okay? Write it just like that. Let A be the set of n in the natural numbers such that the sum of the natural numbers from 1 to n equals n times n plus 1 over 2. So now, rather than saying this formula is true for all natural numbers n, all I have to do is show that the set A equals the set of natural numbers. Okay? And we'll do it by induction. Okay? So our base case. I just need to show, and again, this is very important to understand the difference between your proof that you're writing and the work that you do on the side to figure out how the proof is going to work. So I need to show, and I'm going to write this on the side in gray, that the sum of the first one natural number, in other words, the number 1, I need to show that that equals 1 times 1 plus 1 over 2. Okay? So I think the first step is to see, are you convinced that that's even true in the first place? Okay, so look at it for a minute and decide if you think it's true. Okay, and by figuring out that it's true, you usually work through in your head what is it that you need to write down. In other words, what I mean is, why is that true? That's true because this is 1 times 2 over 2, right? Which is 2 over 2, which is 1, right? Now remember, we've talked before about the logical flow of these things versus the logical flow of your scratch work. All right, so here's another way somebody might write this. Somebody might write, well, 1 equals 2 over 2. And so that's the left side. And the right side can be written like this, 1 times 2 over 2. And those are the same. And so you see a mistake that a lot of people make is they write, notice that, you don't have to use these words, notice that is how I like to start my sentence. Notice that, and a lot of times people will do this. And they'll say, there we go, I'm done with that part. Okay, well, I'm not going to give them full credit for that because I can see several mistakes there. Okay, so what is the mistakes there? Well, you got to remember, we read from top to bottom, right? So somebody's going to be reading this. They're going to read this line here, this sentence, and they're going to say, yeah, okay, that's fine. And then they're going to look at the next line and they're going to read that and they're going to get stuck because it looks like you're just writing down the thing that you're trying to prove, and you're just saying, notice that the thing I would like to prove is true. Okay, which is a bit, I mean, they're going to say, wait a minute, aren't you supposed to show me that that's true? And then this writer's explanation would be, well, because I'm showing you right here, this equals this and this equals this. Well, but the problem with that is that's not how it works, right? If you were writing a story and somebody said, oh, this sentence doesn't make any sense, where did this come from? You wouldn't say, well, that's because you look at the next sentence in order to understand it, the sentence before. That's not how it goes, right? And you might also say, well, no, that's not the whole line because this is not two different lines. You might say, this is just one line. And to that, I would say you're wrong about that. That's different. I know I've done this before. I've done stuff like, let's just say I might have written something like this. Notice that blank, 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 blank equals, whoops, I didn't mean that line to show up, equals blank, 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 which equals blank, 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 blank. You know, we've done that before, and I've said that's one line. But what's the difference? Look at the difference. There's a left side, and then a right side, and then another right side, and so on. That's not what's circled up above. Up above, there's a left side and a right side, and then another left side. That means a new sentence has begun, because a new equation has begun. You see what I'm saying? What's written down here is a string of equations in one sentence. What's written up here are two different equations, which means two different lines of a proof. You see what I'm saying? I don't want to belabor the point, but I do want to make it clear why it's not okay to write this. Okay, so what should I write? I should look at my scratch work, which is there in gray, and I should say, okay, now what's the logical flow? I want to show that this equals this, which means that that equal sign is not already there. So why don't I go ahead and erase it? So how do I get then from here to here? You do it like this. 1 equals 2 over 2, which equals 1 times 2 over 2, which equals 1 times 1 plus 1 over 2. Okay, that's the order I write it in. Notice that 1 equals 2 over 2, which equals 1 times 2 over 2, which equals 1 times 1 plus 1 over 2. And there's my base case. Okay? But remember, I'm wanting to use the language of set theory. So how do I want to write this? Let's just put a comma. That's fine. It doesn't need a new line. Let's just put a comma. And we could say, so the number 1 is in the set A. Okay? I know some of you, probably more than one person, is also in my discrete structures class. And I have not told them how to do this using the language of set theory. If you're in both classes, well, you can do it the way I explained it in discrete structures when you're doing your discrete structures assignments, but I want you to do it this way when you're doing your set theory assignments. If you want to do it this way for both, that would be awesome. Okay, so that's my base case, all right? Now my inductive hypothesis. I write, suppose K is in A for some natural number K. Okay? And then I want to show that K plus 1 is in A. I'm going to write this in gray now because this is scratch work. I want to show that K plus 1 is in A. Which means I want to show that K, I want to show that 1 plus 2 plus 3 plus so on and so on up to K plus 1 equals K plus 1 times K plus 1 plus 1 over 2. That's what I want, okay? Now, I'm going to give you some advice on how to figure this out. This part will almost always be true because of this. So you need to somehow use the fact that K is in A, okay? Now, something else, just some pointers I'm going to give for you, okay? I would advise you to do this. I would put parentheses around that K plus 1, even though mathematically they're not necessary. But just to help yourself remember that this is one number. You had 1 is a single number plus 2 is a single number plus 3 is a single number, and you keep going, and then this is the last number. Okay, so I would do those parentheses. A lot of people like to avoid parentheses whenever they can, but I really think they will help you keep your mind straight. Okay. Second of all, you don't need to write the plus 2 and plus 3. Don't you agree that it would be fine if I would have just written that, right? But what I would very, very, very strongly suggest to you, this is really, to be honest with you, this is the trick right here that makes these problems not very difficult. The trick is write down the term that came before K plus 1. What number is right before K plus 1? I mean natural number here. What natural number is right before K plus 1 would be K, right? Here's the trick between people who find this easy and people who don't. The people who find it easy realize that the trick is to write plus K plus K plus 1, because that's how you pull this into the fray. You see, K is an element of A. That's our inductive hypothesis. So that means that 1 plus ... plus K, that chunk right there, can be replaced with K times K plus 1 over 2. So then we have this. Remember, this equal sign's not really here yet. That's what we want. And we're trying to figure out how to get from here to here. So that equal sign's not really there yet. But I can say this equals this. And at this point, it's just going to be a matter of algebra. What does this equal? Let's just expand it and see. Don't be afraid to just write it out. Wouldn't this be 1/2 K squared plus 1/2 K plus K plus 1? And what would that equal? That would equal 1/2 K squared plus 3/2 K plus 1, right? Now don't forget, here's our goal. We're just trying to bridge the gap from here to here. And each time I go down one line, I'm bridging the gap closer. But always remember, this is our goal. So what do you notice about our goal? It's something over 2, right? So maybe I will factor a 1/2 out of here. And maybe I'll write that as something over 2. What would it be? It would be K squared plus 3K plus 2, right? Not plus 1. Notice that? You see why it would be plus 2 up there? At the end on the top? Remember, here's our goal. I think you might be able to see how we can get there from here. Let's factor the top now. Doesn't that break up into k plus 1 times k plus 2? And isn't that exactly equal to this thing that we are hoping for it to be equal to? And so there's our string of logic. Okay, let me erase this just so that I can write it again. We want to show that this equals this, and the way we're going to do it is to go this equals that, which 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 equals that. That's how we get that equals sign. Okay. Now you might have written more in your scratch work than you need to put in your proof. Like, for instance, is there anywhere we can save some time here? I don't think it is necessary. So here, let me do this for you. I'm going to take that thing, our goal, and let's move it down here. Okay, there we go. Now, I don't think both of these are necessary to write. What's the only difference? Just the k term. I combined 1/2 k plus k into 3/2 k. I don't think that's necessary to break it down into such a subatomic level. You know what I'm saying? So let's, when we do our proof, let's just go from here to here. That'll save us a little bit. Definitely don't cut out this, because that's the major step there. Okay. And then I would go to this. Could you go straight to here? You could. I'm not going to take off points. If somebody skips that step and goes straight to here, I'm not going to take off points. But for me, I wouldn't. I think I'll go ahead and do that. My guess is most of you would probably like to have that one left in there, but to be honest with you, that's maybe one that I would skip. If it were me, I'd probably go straight from here to here. And then obviously your final thing. Now let me show you why I would do it like that. So here's my start. And here's my end. So definitely those are not going to be skipped. Okay. The next line there that I have, that's where I am using the inductive hypothesis. So that's a very, very, very important step. Don't leave that out. And then I expanded. And then rearranged, which in this case, the rearranging was, I factored. So that's why, so I would have exactly those 5 steps. Let me show you. Let's go up there. I would write, then 1 plus ... plus k plus 1 would equal k times k plus 1 over 2 plus k plus 1, which expands into 1/2 k squared plus 3/2 k plus 1, which can be rewritten as k plus 1 times k plus 2 over 2, which is in fact equal to k plus 1 times k plus 1 over 2, comma, so k plus 1 is in the set A. And that's how I would have my formal proof written, like that. Now, if you don't want it to go so long to the right, then feel free at any point to hyphenate it. You know what I mean by that? Like, let's just say that the edge of your page, or the edge of where you feel comfortable writing is maybe right here. Then feel free to just, is it okay if I get rid of the scratch work now? Feel free to just, let's bump this over and take however much you want. Let's say this much. And bring it down here. There you go. Okay. Now maybe that's still, now the next line maybe is too long for your liking. Then just take the end off of that and move it over here. That's fine. I have no problem with that. I know you kind of have to plan it out beforehand. I'm just cutting and moving things around. You can't do that when you've written it in pencil. So you kind of have to plan it out. There you go. Okay. Therefore, A equals N by the principle of mathematical induction. And then we're done. You can stop there. You see how that works? It's brilliant because we have proved infinitely many things there in 3 easy steps. We have proven that the formula we were given works for the number 1, and it also works for the number 2, and it also works for the number 3, and it also works for the number 4, and so on and so on. So we have literally proven infinitely many statements. Okay? So that's mathematical induction. It is just an amazingly brilliant trick. Now, you can't prove that for saying something is true, for instance, for all real numbers. Wouldn't work, because let's say k is a real number. What comes after k? Well, that question can't be answered. When you're doing natural numbers and you say k is a natural number, what comes after k? Then the answer is k plus 1. But with real numbers, there's no such thing as the next real number. No matter how small of a step you take, you've automatically jumped over billions and billions of real numbers. Okay? And we're saying natural numbers here because that's the way it is in the book, but this can be done for integers as well. Maybe you had something that's true for all integers starting with -10. Then your base case would be -10. Your inductive hypothesis would be k. So you would show -10 is in A. You would say, suppose k is in A for some integer k, and then show that k plus 1 would be in A. Okay? It's a brilliant technique. I don't remember right now who came up with it. But I think it's one of the more brilliant things of, if I had to make a short list of the, not necessarily the most important things in mathematical history, but maybe a short list of the things that are seemingly simple and yet are tremendously important, then proof by induction would definitely be on that list. Okay, that's all for today.